I'm going to discuss yet another important aspect of physics, which is negotiating a circular trajectory. If you're in a vehicle and you want to negotiate a circular trajectory, what enables that negotiation? What enables that negotiation? What are the pitfalls? How do we overcome that? And a parametric discussion of the same. Typically, in a very simplistic, naive fashion, if you are trying to undergo a circular trajectory with a velocity v, and you are not aided by anything, to execute this circular trajectory. You are not aided by anything to execute this circular trajectory. You would move radially outwards. You will not be able to execute the circular trajectory if this surface, or you did not have an aid that could enable that circle, because a circular trajectory will require a centripetal force, right? So this is a circular trajectory and you want to be aided to execute this circular trajectory, right? This is the center of the circle, radius r. You have a likelihood of skidding outside. There is a tendency for you to skid away. There is a skidding which is prospective. So you need something that will give you the required centripetal force. You need, how much of centripetal force you need? mv squared by r, right? And if friction is competent enough, it will give you that centripetal force. In the simplest form, friction would try to provide this centripetal force. If V is not very large, or R is not very small, or if M is not very large, as long as friction is, requirement of friction is to the tune less than or equal to maximum static, it will give you the required centripetal force. It will give you the required centripetal force to negotiate the circular trajectory. But it's not like if you go on increasing V, F will keep pace with you. No. F has a limit. So which means, only those V's, M's and R's are acceptable for which F does not exceed maximum static friction, say mu mg. Mg is downwards, N is upwards, so N is mg here. Mu s is the maximum static friction, coefficient of static friction, so this is maximum static friction, right? So which means now there is a limit on V, for example. So you have a road which is already made. There is a road which has a circular pathway. So you are not going to, tamper with the radius of the road. Corporation people will come and bang on you, right? You can't do that. You have a mass. All of a sudden, you're not going to, weed out your flesh and say, okay, now I'm light. No, you're not right. You can't do that. But you have control over V. So you say, all right, I'll try to keep my V small, so that friction, my friend who's trying to help me, will actually be able to help me to negotiate this circular trajectory. And I don't skid away to glory, right? So you say, all right, if I use this, then a thumb rule calculation here is like V not exceeding root mu s gr, right? This is what it gives me. That means this is the maximum velocity with which you can negotiate a circular trajectory of radius r, where the turf has coefficient of friction mu s. You can't change mu s, right? That's a property of the turf laid out by contractors, isn't it? So this is the upper limit of the velocity with which you can negotiate a circular trajectory of radius r, which provides to you some aid in the form of friction, whose property is given by mu s, right? But you want velocities larger than that. You want velocities larger than this. What then needs to be done? So what they did was they said, all right, one way to accomplish this. So this has a lot of dependence on friction, isn't it? This model has a lot of dependence on friction. You want to mitigate that dependence on friction. So one way that could be done is that the road, which is circular in character, is slightly raised above the ground, in the sense that the road, say, think of it like a stadium. This is my road, and this is like the circular trajectory you're trying to negotiate. And this road all over the place, it's like a frustum of a cone. It's like a frustum of a cone in a certain sense. And the road is not horizontal, is raised at an angle theta. This is called a banking of the road. Now, how does it help? So we then say we have banked the road. We have slightly raised it, lifted it. This is my road. All over is the road like this, like a frustum of a cone. Surface of a frustum of a cone. This is the radius r of the circular trajectory which you are trying to negotiate. Right? V, for example, comes out of the plane of the board in this case, like this, right? V is like this. You would require centripetal force mv squared by r directed towards O. Yes or no? If V is like this along the tangent to the circle, then mv squared by r is directed towards O, the centripetal force. You need centripetal force, and now that's your need. To negotiate this circular trajectory on a banked road. This is a circular trajectory on a banked road. Can you visualize this? Now, who, why, and where will give you this? Let's see. Assuming to begin with that we want to break free from our dependence on friction. This is my banked road. And I'm negotiating this circular trajectory of radius r with a speed v. And forces, I imagine myself or yourself to be a point particle for convenience. Weight acting downwards. Right? Then the road will offer normal reaction to you, which would be at an angle theta with the vertical. Right? These are the two forces acting on you. Yes or no? N could be resolved as n cos theta vertically and n sin theta horizontally. N sin theta, our friend, is directed towards O, the center of the circle. It's directed towards the center of the circle, and we are relying on n sin theta to provide us the necessary centripetal force. We are relying on n sin theta to give us the required centripetal force to negotiate this circular trajectory on this banked road. On this banked means raised road. Right now? So, how much of centripetal force do I need? I need centripetal force directed towards O, mv squared by r. And who am I counting on to provide this? N sine theta, right? So, n sine theta providing this mv squared by r. And you don't want to fall down. You want to stick to this plane of the circle. So you want vertical components to cancel off so that you're not accelerated in the vertical direction while negotiating the circular trajectory, right? So you want n cos theta to take care of weight, right? Right? And this combination of V, R and theta, I'm able to negotiate the circular trajectory, and it's only normal reaction which is coming and providing us the requirement, right? So if I divide this by this, I get tan theta equal to V squared by GR That means theta, which is the banking of the road, prefixed banking of the road, R is the radius that you want to negotiate on that banked road, R is the radius that you want to negotiate on that banked road, and V is the velocity with which you would negotiate that radius on the banked road. They are related by this equation. That means V is, as you can see, root GR tan theta. Now this is part of the specification of the banking. This is part of the specification of the banking. They'll tell you this is a road banked at an angle theta for a radius r. You can negotiate a velocity v. You can have a velocity v for a radius r on the banked road banked at an angle theta. But you want to, let's say, move with a velocity less than this v. You want to move with a velocity less than this v. What do? Suppose v is decreased. That means r will decrease. R will decrease. Now very clearly, if you move to a circular trajectory lower than this, then you'll have a smaller radius. Yes or no? Right? So then the circular trajectory that you must negotiate would be this. For a small, this will be smaller r, isn't it? This will be smaller r than this. That means it will fall down. It will fall down. If v is smaller, then r has to decrease. R has to decrease. If v equal to root gr tan theta is for this trajectory. But if you decrease v to smaller than root gr tan theta, then if v is smaller than this number, then r has to be smaller than this r. Yes or no? That means it will fall down. The vehicle will fall down and will then negotiate a circular trajectory of radius less than this r. But if v is increased more than this, then r has to increase. R has to increase. Then the vehicle would have to negotiate a circular trajectory higher than this. This is for root gr tan theta. This is for v naught, which is root gr tan theta. Root gr tan theta is v naught. Trajectories above this will be v greater than v naught. Trajectories below this will be v less than v naught. As r increases, well, normal reaction can provide greater centripetal force. Higher v's. These are lower v's. These are lower v's. And this is the specified r. Specified v root gr tan theta for that banking. Yes or no? right? So in this case, there isn't dependence on friction. There isn't dependence on friction. But however, it's not like the banked roads will be smooth. And it's not like, if you're moving with, you can't do while driving or while running along that circular trajectory, will you do this calculation? I mean, you won't calculate a root GR tan theta and, obtain your radius and everything. What would be appropriate, move up, move down? You can't do that, right? Right? Eventually, you will have to, you can move with any velocity. Which means the only thing is, if you are moving with a velocity different from root GR tan theta along a circular radius different from this R, you will, so this is what normal reaction could have done. Without depending on anything else, the normal reaction could have enabled you move in a circular trajectory of radius R with a velocity root GR tan theta. But your velocity could have been larger than root GR tan theta. Your velocity could have been less than root GR tan theta. What do? That is when the deficit or the excess is taken care of by friction. Let us see how. This is the velocity which will be completely handled by normal reaction. Normal reaction says, oh, I'm good enough to take care of this velocity at this radius. Anything larger than this velocity or smaller than this velocity, it falls back on its deputy, the friction. Friction will then come and do the needful to the extent it can. Do you understand the basic premise? Now let us see how that happens. Let us see how that happens. Clear? You don't want to change R. You don't want to calculate a V while driving. Right? Isn't it? Look, this is my banked road. This is the banked road. Circular trajectory. And I'm negotiating this circular trajectory with a speed v. Right? And like I said, this would be the normal reaction. And the radius of this circle is R. The radius of the circle is R. Clear? Now if this is a normal reaction N, the radius of the circle is R. Evidently what we have seen is, if V is root GR tan theta, then normal reaction good enough, N good enough. No other support required. No other support required. Friction not required. F not required. Friction is a very self-respecting fellow. When not required, it will not come in. It will not come to you uninvited. Only when you ask for help, one kind or the other, it will come in. Right? So good. This is my standard condition. But suppose V, so this is my V naught. V equal to V naught. V is equal to V naught, which is root GR tan theta. But suppose the speed with which I want to negotiate the same radius R, is greater than this V naught. Is greater than this V naught. Right? V is greater than this V naught. That means you require greater centripetal force. Than above. Right? If V becomes more than this V naught, then the centripetal force mv squared by r will be larger that you require. Yes or no? This is V equal to V naught, and now I have V greater than V naught. This is my normal reaction N, which makes an angle theta with the vertical. This is my normal reaction N, which makes an angle theta with the vertical. But no, you need more centripetal force now. You need more centripetal force because the velocity has increased more than root gr tan theta. If you need more centripetal force, then what happens is friction acts in this direction, its component in this direction provides the deficit. Its component in this direction provides the deficit. This is what happens. You know what I'm saying? That means friction. If you want to move with a velocity more than V naught, friction acts downwards so that it has a radial component which augments the radial component of N and provides the required centripetal force. Are you able to understand everything that I'm saying? So if V is more than V naught, friction will act down this incline, right? And if V is less than V naught, this is N, making an angle theta with the vertical. This is theta. This is friction. Okay, friction I do not know. If V is less than V naught, then the centripetal force mv squared by r decreases. If V is less than V naught, then you need less amount of centripetal force than what you needed here. Yes or no? So then friction says, hey, I'll act upwards. Then friction acts upwards. If V is less than root gr tan theta, friction acts upwards. So that the component of n sin theta is partially diluted by the component of f horizontally, and the centripetal force is lesser. So if V is less than V naught, friction acts outwards like this. If V is more than V naught, friction acts downwards or inwards. They call this inwards, they call this outwards. This is the case where the velocity is less than root gr tan theta, friction has to act outwards because now it needs lesser amount of centripetal force. There is a component of F in this direction which dilutes the centripetal force, right? If V is more than V naught, then you need more centripetal force than this case. Friction then helps and aids providing that differential. Yes or no? So suppose V is less than V naught. V is less than root gr tan theta. Friction realize is going to act like this, right? And this is theta, so this will be theta, corresponding angles, right? Friction then could have been resolved as friction as vertical component f sin theta, horizontal component f cos theta. This is V less than V naught, and there is mg acting like this. Yes or no? Now, n sin theta, component of n in this direction, minus f cos theta will provide the required centripetal force, isn't it? N sin theta minus f cos theta provides the required centripetal force mv squared by r. Yes or no? N sin theta minus f cos theta provides the required centripetal force mv squared by r. and vertical components, n cos theta plus f sin theta must balance the weight. N cos theta, component of n in this direction, plus f sin theta must provide the weight, right? So n cos theta plus f sin theta must take care of the weight, mg. So v is less than v naught, where v naught is root gr tan theta. Yes or no? So far so good. Now, so I am operating at a velocity which is less than root gr tan theta. Friction acts upwards like this, or outwards, so to say, and these are my governing equations. This is the centripetal force equation, this is balancing the weight, right? Now, suppose I increase v. Suppose I increase v. V is initially less than v naught, less than root gr tan theta. Now I increase v. From this point onwards, I am operating with a small velocity v naught, much smaller than v naught. And now I gradually increase the velocity of the particle. Now I gradually increase the velocity of the particle. So my centripetal force requirement would increase. N and F will have to therefore remodel themselves. So mv squared by r will increase, the requirement mv squared by r will increase. The requirement mv squared by r will increase, yes or no? Right? Now to meet this requirement, in how many ways can I meet this requirement? Either I increase n and f remains same. One possibility is increase n and f remains same. That's one way. This requirement could be met. By increasing n and causing f to remain same. That's one way it could be met, so that this difference is larger. The second way it could be met is n remaining same and f decreasing, friction decreasing. That's another way this requirement could be met. The third way it could be met is n increases and f decreases. N increases and f decreases. F decreases. That way also this difference will increase. Yes or no? These are three models. These are three models. See, theta, I can't do anything to theta. Those guys have constructed the road with that theta. So theta is not changing. So if this number has to increase, I have only handle over n and f. I can't change theta, isn't it? So this difference has to increase. That means I have to play around with values of n and f. So to increase this difference, I increase the value of n and f remains the same. Then difference can increase. Huh? No, it's less than that. It's static friction. If f had reached maximum, it will start to skid. That's the whole objective. I don't want the fellow to skid. I wanted the fellow to have a smooth ride on the circle. Right? It's not mu n. Clear? It's not mu n. It's less than mu n. Right? So, n increases, f remains the same. That's one way this difference can increase and the centripetal force requirement could be met. Or n remains the same and f decreases, static friction decreases, then also this difference can be increased. Or n increases and f decreases, the compound difference increases. Three models, right? But no matter what, this condition will always remain preserved. N cos theta plus f sin theta at all times for all n and f that are pertinent must balance the weight. Right? Now, look at this. If n increases but f remains the same, then this difference increases. It will become more than the weight. Right? So I can't have A, because in A, this will not be maintained equal to the weight. If n increases and f remains the same, This will become more than mg, isn't it? So ruled out. N remaining the same and f decreasing, then this will become less than mg. Can't happen. Junk. This second condition B. Junk this second condition B. I can't have these two because it will not be commensurate with this requirement of balancing the weight. And therefore, the only possibility is n increases and f decreases. N increases and f decreases. Yes or no? So simultaneously, if I start with a small value of v smaller than root g r tan theta and I gradually increase v, what happens? N increases and f decreases. N increases and f decreases. Right? Now, I come to a state. So v was originally less than root g r tan theta. I come to a point where v becomes equal to root g r tan theta. And that means then I arrive at this case, v equal to root g r tan theta, then friction becomes 0. Friction becomes 0. I start with a velocity smaller than root g r tan theta. Friction is outwards. And I then go on increasing the velocity. I'm still smaller than root g r tan theta. Friction will act like this and it will decrease. If I'm increasing the velocity, friction will decrease. Then I come to a velocity which then happens to be root g r tan theta. Velocity becomes root g r tan theta. Means what? Friction will become 0 because normal reaction all by itself can handle root g r tan theta. Yes or no? So root g r tan theta is handled by normal reaction. Friction will become 0. In my attempt to increase v starting with a value much smaller than root g r tan theta, I reach a state of root g r tan theta. Friction decreases gradually and eventually becomes 0. And then I get more ambitious. My velocity becomes more than root g r tan theta. And then friction says, now you can't live without me. Friction acts like this. It augments the centripetal force and enables this circular trajectory. Enables you negotiate this circular trajectory. Friction, that means it decreases, means according to this equation it will become negative because it goes downward. It goes downward. Right? This is what happens. This is how banking works. This is the basic physics of banking of curves. Basic physics of banking of curves. Root g r tan theta, good enough for normal reaction to handle. It's a specification of the road. The road makers will specify that we have banked the road at an angle theta to negotiate a circle of trajectory r, radius r, with a velocity root g r tan theta. But obviously you could have had a velocity smaller than root g r tan theta. R cannot be changed. So there is an interplay between n and f. You could have had a velocity greater than root g r tan theta. You can't change theta, you can't change r. And you want a velocity more than root g r tan theta. What the heck? Again, there is interplay between n and f. F changes direction, changes magnitude, accommodates commensurate with your requirement. Yes or no? This is the story of banking of curves. Do you all understand all that I have said and for all times to come? Right?